All right, hello there to those of you watching the recording. Got some web work questions here. All right. So, how many elements are in the union of four sets? If each set has 97, each pair shares 53, the triples share 20, and two elements are in all four. Okay, so what do you guys think? How should we approach this question? Yep, we did something like this before. Yep, it's a Venn diagram. That's right. You can also use a formula. You don't have to use a Venn diagram, but you can do it either way.
So I haven't actually done this problem, but I remember last time when we drew out, I think it was the question that was like American food, Italian food, and Mexican food or something like that.
Yeah, exactly.
So we drew like a Venn diagram and it was like, oh, this has 97 elements. Each pair shares 53. So you do the 53 in the like overlapping sections and you can kind of figure out what's in the middle. Yeah, I know there was a little trick to it, but it's that problem that I'm thinking of.
Yeah, that's right. And you can kind of work from the inside out. So, you know, if you want to do a Venn diagram, I guess let me stop sharing here and video. There we go. Okay, great. So if you have four sets, first of all, this is not a Venn diagram for four sets, just to be clear. Be careful here, because so we want to go through there and there. Yep, there we go. All right, that is not a Venn diagram for four sets. Why? Oh, crap, and I missed. Here, let me make it bigger. Yeah, the diagonal ones don't overlap. That's exactly right. So here we want some of that to be there. There we go. That's better. Yeah. So like this, right? Sets A and D don't have a section where only A and D are overlapping, right? So this is not a Venn diagram for four sets, right? You can draw a Venn diagram for four sets if you want, but that's not it. Does anyone know how to draw it? Any ideas? Okay, well then let's take a look, right? So turn that off, that on. So as usual, Google, right? You'll notice this one, right, is what we did, and that's not right because the yellow and the green circles don't have a section. But this, on the other hand, 1, 2, 3, 4, yep, this one, these sort of ovals that overlap here, this is a Venn diagram for four sets. Right? And now AD has a section right there, right? So you can draw it this way, and that's fine. And if you want to do that, maybe I should get an empty one. Oh, and here's another way to do it. This way is kind of nice, right? So A and B are these sort of house-looking objects, and then C and D are these sort of, I don't know, crayon-looking objects, right? And here, there's enough to have all the overlaps, right? So maybe I can draw it this way. So let's see if I can see if I can work that out. So we've got, so let me pop back over here. All right, so we've got A and B. And then we've got C and D. Okay. So here's where all four sets overlap, right? And we said there's going to be two elements in there, right? Now, each triple of sets shares 20 elements, right? Including the two in the middle. So here's the triple overlaps. There's, let me label these. There's A, B, C, and D, right? So this is ABC. That's a triple overlap. Here's ADC. Here's BCD. And here's DAB, right? So these four are the triple overlaps, and how many elements are going to be in each one of those? So if there's 20 elements in the triple overlap and 2 elements in the quadruple overlap, how many will be remaining in each of these triple overlaps? So do you guys not see what's going on here? Is everybody lost? I thought that would be an easy question. Yeah, overlap minus 2, right? So there's 18. Yeah, perfect, good. So there's 18 in each one of these. Okay, so now the next sets that we fill in are the double overlaps, right? Like AB or CB or something like that. Each pair of sets share 53 elements, right? So how much are we going to put into the double overlaps, like AC, AB, right? BC. I guess this one would be what? That one would be BD. How many would go in there? Okay, so 53 minus 18 minus 18 minus 2. Cool. Okay, so how much is that? That's 51 minus 36. 15, right? Yep, 15. Okay, so 15 in here, 15, 15, 15, 15, 15. Okay, good. And then how much is going to be in each of the single sections? All right, so I think except it was 97, not 96, but yeah, that's the right idea. So we have 97 minus 3, like let's take A for example. So here's the set A, it's got all this stuff in it with a total of 97, right? So, oh, yours is a little different. Okay, yeah, that's fine. So it's going to be the total amount minus all the junk inside, which you said exactly right, Sean, minus 3 15s, oh, almost right. There are 3 18s in here. So you would subtract off 3 15s and 3 18s and then the 2, right? So let's see, 97, let me do a calculator here. 97 minus 3 times 15 minus 3 times 18 minus 2. -4. Uh-oh. Well, that ain't good. Well, something went wrong. Because obviously we can't have a negative number in here. What happened? Any ideas? Well, I put too much in the triple or the double, right? Okay, I agree. Well, it seems pretty obvious that this one should be 18, right? Because if there's, if there's 20 total and then there's 2 in the all 4, well, it should just be 20 minus 2, right? So that seems that should be right, I think, right? Maybe something went wrong with the 53. Right, so should we be subtracting off? Should we be subtracting off more from the 53? Okay, let's try to do a little coloring. Maybe that'll help. Okay, so if we're trying to find the pair overlap, right, for A and B, right? Or here, why don't we just add the colors, add the numbers back up and see if we get 53 out. That's a good idea, right? So we're supposed to get in the pair of A and B, right, we're supposed to get 53. So where do A and B overlap? Well, that's going to be right here is where A and B overlap, right? We're supposed to have 53 in there. Yeah? So what do we got? So we got 20, 38, 48, 53. Nope, that seems right. Interesting. Okay, so that did add up to 53. Other ideas? I mean, maybe one of the other overlaps is, maybe we subtracted something too many times. Well, here's another idea. What maybe one of the other overlaps is messed up. Like, let's check BC, right? So the BC overlap is here, right? But that's the same thing as before. 2 18s, a 15, and a 2. Right? It's the same thing that we had on this yellow strip here. So, maybe the question meant something different than what we thought it meant. If we go back to the question, okay, it says, if each of the sets has 97 elements, each pair of sets share 53, each triple share 20, and there are 2 elements in all 4 sets. Okay, so in that case, like, is there a different way of interpreting this question?
When we do 20 elements in the triple, do we have to subtract 2 and then divide by 2? Because it's going into 2 different slots that are going to be in the triple?
Well, it says each triple of sets shares 20 elements.
Okay, and there's 4 triples of sets.
Right.
Yeah,
right.
okay.
So, I mean, you could think of it in a different way and say, well, okay, there's 2 in the middle, and then the triple, you don't subtract the 2, right? It's just, the question just means the triple by itself, not including the 2 in the middle. You could interpret it that way. I mean, what would our answer be in that case, right? Then we would have, if we're not supposed to be subtracting stuff, right? Then we would have 97, and then how many pairs of sets are there? Well, there would be 6, right? So it'd be 4 times 97, 6 times 53, 4 times 20, and 2, right? So maybe that's the answer. So if we did 4 times 97 plus 6 times 53 plus 4 times 20 plus 2. Nope. So that's not the way to do it. Let's see what the answer is supposed to be here. 148. Okay. Well, how are we doing here, right? So with our picture, let's see where we're at. We can at least work backward and try to find what the answer is and try to figure out why, right? So we have 15 times 6, 18 times 4, and 2. Okay. So in that case, how much is left to be in each of these sections, right? So we would have, let's see, 6 times 15, 18 times 4, and we're going to do 148 minus those guys. It does say negative 16. Maybe the question is broken because if the total is supposed to be 148, right, then that does go along with the math that we did so far, because what's happening here is when we add up all these guys, right, we get more than 148 already. So we would have like negative 4s in here, which really shouldn't happen. We shouldn't ever have a negative amount of items in the set, right? So what do you guys think? Think it's do you think the problem's broken? You think we did something wrong?
So it could be that when it says each triple of sets shares 20 elements in this case, right? Okay. It could be that it means that like A, B, C, and like A, B, and B, C are 20 altogether.
Mm-hmm.
Like we're overcounting somewhere, and I think it's just because they've used the word triple in a kind of vague way.
Yeah, so, but it does say each triple of sets shares 20 elements. So I don't
It's
think they're saying that all the triples have 20 elements total.
sure. I mean, clearly the problem's either broken or there's something weird about the wording of it, right?
Yeah, yeah. Yeah, there's something funky going on. And if what my guess is that WebWork is picking different numbers for different people. Maybe the numbers that they're picking, some of them will give you all positive numbers like you're supposed to have, and then maybe the ranges are wrong and you're getting negative numbers somewhere. Um, so let me look into that, and I'll get back to you on that. As for right now, I think if you just allow for there to be negative numbers in here, it seems like you will still get the right answer, but there really shouldn't be negative numbers in these guys, right? Um, so I would say do it with the negative numbers and you'll probably get the right answer. And I'll check up on that problem and see if in fact it is broken. Yeah. Any questions about that? All right. Speaking of broken questions, I was not able to fix those broken ones last week, so I'm just going to skip those questions for your grading. So not to worry about that. And you had a couple other questions, Haruka, of 6 and 9. Was that right? Back here. Yep, 6 and 9. Okay. So let's stop that and go over here. All right. All right. All right. 5-card poker hand is dealt at random from a standard deck. Note that the possible number of hands is 52 choose 5, which is almost 2.6 million. Find the following scenarios. What's the probability that your hand has an ace? It's alpha divided by the total. Okay, especially B and C. Okay. Um, so let's start with A, right? What's the probability that the hand contains an ace? Well, first of all, what does probability mean? Someone want to explain that? The likelihood of something to happen out of the total things that could happen, right? Um, yeah, the chance that you get a specific thing out of some total number of things. Well, the total number of things is right here. That's the total number of hands you could get, all the possible different hands, 2.6 million, right? And what you do is you take the ones that you're looking for, which is we're calling alpha in this case, and you divide by the total number, right? Probability is essentially just division, right? Okay, so how many different ways can you get a hand with an ace in it, right? That's what they're asking for. That's alpha, right? Because you have all the different ways you could get a hand with an ace divided by all the different hands total, right? The ones with an ace and without an ace, both, right? So how many different ways can you, how would you compute how many different ways you can get a hand with an ace in it? Okay. 48 choose 4 times 4. Okay, so how did you get that, Haruka? Can you explain? Okay, there's 4 aces, and then you choose 4 other cards, right? So first of all, you have to have an ace, and there are 4 aces because there's, clubs, hearts, diamonds, spades. So there's 4 choices there. And then you have to choose 4 other cards from the remaining 48 cards, right? from the remaining 48. Why is there 48 cards remaining? Because those are all the non-aces, right? Because you have to have exactly one ace. You can't have, more than one ace, right? So there's 48 non-ace cards remaining in the deck, and you're picking 4 of them. Yeah, very nice. Okay, so so if we do the computation there, what do we get? I could type it out, but it looks like Haruka, you got the answer. What's the numeric answer there? Or should I just compute it? Here. Google will do this. Nah, it doesn't look like it. How about this? There we go. All right, so 778,320. So for Google, the choose notation is just the first number and then the word choose and then the second number, right? That's the notation Google wants there. Okay, so let's see if that worked. Yep, looks good. Okay, so let's try B and C. So what's the probability that the hand is a flush, which means that all the cards are the same suit? Okay, so again, we're dividing by that same total here, but how do we count up how many ways you can get a flush? Any ideas? So you have to think about what you can pick, right? So what different things do you get to pick if you were gonna construct all the different flushes, right? There's a few different things you'd have to pick in order to get that flush. So what's the most important thing you'd have to pick? Okay, so the most important thing would be what suit is it, right? So how many different suits are there? Right, 4 suits, 13 cards each. So we're gonna have 4 different suits that we're gonna pick, right? So we actually have 4 times already. But then what else are we gonna pick? After let's say that we're gonna have a flush of hearts, right? Then you have, well, you pick one of those, you have 12 left and so on. It's true, but there's a little bit nicer way of doing that, right? So once you pick a suit, there's 13 cards in that suit. So close, 13 choose 5. Oh boy, uh-oh. 13 choose 5. Why would that be? Any ideas? So here you have 13 cards in that suit that you've chosen, and you're picking 5 of them because you have 5 cards in your hand, right? So first you pick your suit. There's 4 options. Then of the 13 cards in that suit, you pick 5 of them. So choose is how many ways you can make something out of something. In this case, how many ways can you make 5 out of 13 choices, right? Choices, right? That's why choose, yeah? So, right, 13 choices, and you're actually choosing 5 of them. Yeah. Questions? Oops. You don't need to worry about how many cards are left in the deck because the problem has set that up already. Yes, that's right. So it's 5148, I think, right? Okay, looks good. Any questions on that one? Seems like people are either sleepy or very confused. What's going on? Is everyone following here? Making sense? Or I mean, we haven't covered choose notation yet. Obviously, we haven't done that part of the lecture, but so if people are lost, that's fine. Okay, well, I'm gonna plunge forward unless people have questions for me. Not familiar with choose notation. Cool, that's fine. Yeah, we're gonna talk all about that today. Great. Okay, so let's see if we can do this last one. What's the probability that the hand is a straight flush? Okay, so what are we picking? Well, first of all, what's a straight flush? What does that mean? All in suit and order, right? So first of all, we're going to pick the suit, right? Which is 4 choices again. But now, since all the cards are in order, how many ways can we have 5 cards in order? Okay, so can someone give me an example of a straight? What's an example of a straight?
2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts.
Good. 2, 3, 4, 5, 6, right, is one example. What's another example of a straight? What's the high straight? So that was the lowest straight, 2, 3, 4, 5, 6. What's the highest straight? 10, Jack, Queen, King, Ace. Perfect. So how many different straights are there? 9, right? 2 through 10 inclusive, so 9 total. Yeah, we're not going to count straights that loop around. Yeah, that's against the rules. Right? So we would have 4 times 9, right, for a straight flush. And let's see if we got it. Oh, didn't like that one. Uh-oh. It says 40. Maybe you can use ace as a low card or a high card. I guess that must be the answer, right? So they must be doing the rule where ace can be low or high, right? In which case you would have straights from ace, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So yeah, so I think they're just thinking about the sort of like house rule where ace can be low or high. That would be my guess. Yeah. Does that answer your question, Haruka? So it'd be ace, 2, 3, 4, 5, right? You don't know why they. Yeah. So it's I think that's just like a common house rule in poker. Yeah. So it'd be 4 times 10 exactly. Okay. Cool. Any other questions on that? Okay, so why is the total number of possible hands 2.6 million? Well, that's because you have 52 choices and you're choosing 5 things, right? So the total number of hands would be 52 choose 5, which is actually what they said on here, right? They were saying, choose 52 5. Oh, that's almost right, but that's not totally right, Nathan. So the definition of choose is going to be a factorial. So the first number factorial divided by the first number minus the second times the second number factorial, right? So actually what we would be doing there is 52 factorial divided by 52 minus 5 factorial divided by 5 factorial. There's another term in the denominator that you had forgotten there, Nathan. And I think that was your mistake. Yep, and there's our answer. Yeah, you just look at the formula for choose, and I think you'll see that there, Nathan. Does that make sense? That's a great question. So you have 52 factors. So why is the choose formula what it is? I think is your question, right? And the way to think about this is say, okay, well, I have 52 different things, and I'm going to pick 5 of them, right? So what you're going to do is you're going to say, okay, so I have 52 choices for my first card. Let's think about drawing the cards in order, right? So I'm going to have 52 choices for the first one, 51 choices for the next one, then 50 choices, then 49, then 48, right? Because each time you draw a card, there's less cards remaining in the deck, so the number of options that you're drawing from decreases by 1 for each card that you pick, right? So you had that, Nathan, I think, right? That part made sense? Yeah, okay. So that did make sense. It is like permutations, but the difference is, let's say, for the sake of argument, that you drew a straight flush. You drew 2, 3, 4, 5, 6, all of hearts, right? Now what happens there is if you draw the 2 of hearts, then the 3 of hearts, then the 4 of hearts, all in order, okay? That's the same hand that you get at the end of the day if you draw them in a different order. You could first draw the 4 of hearts, then the 2 of hearts, then the 3 of hearts, then the 6, then the 5. And the hand that you get is going to be the same no matter what order you draw the cards in. Right? So you were right to mention permutations. It's like permutations. The difference between them is that the order doesn't matter. Right? With a permutation, the order does matter, but with a combination, which is what we're talking about here, with a combination, the order doesn't matter. Right? No matter which order you draw the cards, you still have the same hand. Right? And so this extra dividing by 5 factorial is accounting for the fact that no matter what order you draw things in, you get the same hand. Because how many ways could you draw the cards, right? Well, 5 factorial. Imagine if you're drawing cards and you say, okay, well, I'm going to draw these 5 cards, but I'm going to do these 5 things, okay? How many different orders can I do these 5 things in, right? Well, the first thing you could do, again, you're picking, right? For the first thing that you want to do, the first card that you're going to draw, you have 5 choices because you haven't done anything yet. So you have 5 choices for your first thing. But then for the second thing, you've done one of those things already. So you only have 4 choices left. And you keep going down, right? So it'd be 5 times 4 times 3 times 2 times 1 is the total number of orders. And we're dividing by that to sort of get rid of them because the order doesn't matter, right? So that's why we're dividing by that to say, oh, well, before with this guy, we had said, well, 2, 3, 4, 5, 6 is different than 6, 5, 4, 3, 2, which is different than, 2, 4, 6, 5, 3, and whatever other order you want, right? And those orders are taken into account here, but then you get rid of them by dividing by how many total or possible orders there are for that last step. Does that make sense, Nathan? Does that answer your question? Nice. Excellent. Okay. Yeah, sure. Well, I hope it says it somewhere, but maybe not, right? When I find where it says that, I'll be sure to point it out to you. Haruka, you said, I think we have much more sets like 5, 4, 3, 2, 1, or 1, 3, 2. Okay, so if the order is not important, so the answer should be more than 40. Oh, you mean for problem 6 here from a moment ago? This guy here? Yeah, so it's not exactly, right? Because even though the order is not important, I didn't count the order as being important for the straight flush, right? All I said was, okay, I'm going to pick a suit and I'm going to pick where the straight starts, right? And none of those have anything to do with the order of the cards, right? So those two choices that I made actually was not including the order of the cards in that. So it actually was right the first time. The only thing that I can imagine, since instead of 4 times 9, we were supposed to get 4 times 10, is that there must just be one more starting point for our straight, which must mean that, ace can be played low or high. Does that make sense, Haruka? Cool. Okay. And 9 was the last one you wanted to see. All right. Union type questions, okay? How many bit strings of length 7 either begin with 2 zeros or end with 2 ones? Okay, so let's do the first part first. How many bit strings of length 7 begin with 2 zeros? What do you guys think? So bit strings just mean sequences of zeros and ones. So for example, a bit string that began with 2 zeros would be 00110110. Right? That would be a bit string that begins with 2 zeros. Yeah? So how many bit strings begin with 2 zeros? Two to the fifth. Good. So 2 to the fifth of them begin with 2 zeros. How many end with 2 ones? Also 2 to the fifth. Good. But there's some overlap because some bit strings start with 2 zeros and end with 2 ones, and we wouldn't want to double count those, right? Inclusive or, it could be either one or both, right? So we are supposed to include the strings that begin with 2 zeros and end with 2 ones, but we don't want to double count them, right? And if we've already counted some of the strings that do both in our counting of the ones that start with 2 zeros, and we count the ones that do both in our counting of the strings that end with 2 ones, then we've double counted. So at the end of the day, we need to subtract off the number of strings that begin with 2 zeros and end with 2 ones in order to get the right amount. Since we double counted it, we need to subtract off one more thingy's worth. So it'd be 32 plus 32 minus what? How many bit strings do both begin with 2 0? Yeah, 2 cubed, 8. Perfect. Yeah, good job, guys. Okay, so let's check and see if we're right. Nice. Okay, so let's try the next one. Every student in a discrete math class is either computer science or math major or joint in both subjects. Okay. How many students are in the class if there's 30 CS majors, including joint majors, 30 math majors, including joint majors, and 7 joint majors? What do you guys think? 53, right? Because it'll be 30 plus 30 minus the one that we double counted, which is 7 of them. There we are. Okay, any other questions there? Okay. That's right. Yeah. Well, if you're good at the probability section, you'll never step foot inside a casino again because you'll realize that it's throwing away your money, right? Or maybe you'll walk in with just, you know, however much money you can afford to throw away, right? Like 20 bucks, right? That's fine. The right way to gamble, well, I won't say the right way. The most financially responsible way to gamble is to look at it like you're paying for entertainment, right? So if you're paying 20 bucks an hour to be entertained, okay, that's fine. That's you know, you do you, right? Um, but if you're looking at it like you're going to be you know, get rich, you're not. You're going to get poor. That's why casinos are rich, right? Because they take your money. That's why they have all the free drinks and the um, fancy big fancy displays in there that cost millions of dollars, right? That money came from all the people that gambled and lost all their money to them, right? Um, yeah, well, stock trading is yes. The thing with stock trading, though, is that the game is not rigged against you in the same way that a casino is. A casino is very careful about how they rig the game against you, right? Whereas the stock market is not rigged in the same way, rigged in a different way, a lot of other ways, but it is different. Um, uh, sure, yeah. So there are ways to cheat a casino, but if they catch you, then you're going to go to jail. So not not the best plan, right? Um, you know, maybe you can get away with it, but you know, I wouldn't do it personally. I think there's better ways to make money than trying to cheat a casino. um, uh, exactly. Yeah. So that's right, Sean. Even if you're counting cards with perfect strategy, you're only you know 1% above you know just chance, right? Yeah, and that's right, David. Yeah, there's been a variety of different things that casinos have done to try to stop people from doing that. Um, yeah, definitely. Yeah, okay. Um, cool. So, any other web work questions before we jump into the book material? Oh, and you know what? There was a question in my email about that union thing from our lab last week. So let me do that as well. Actually, need to download it first. Okay, lab 3. Yeah, so I was going to show you how to correctly do unions in your lab from last week. Did anyone figure it out? You got it to work with greater than, less than. Okay. Yeah, some things will work, absolutely. Some things will not. So there are, you know, a couple examples there in the different relations that I showed you, right, where it works for some of them, but not others, right? So let's go through and we'll look at some of those examples, right? See if did anyone figure out why it wasn't working sometimes? You did plus minus with. I'm going to have to look at the variables, Lucas. I don't remember what all those things are. Okay, here we go. So, okay, so this one isn't working, right? So here, let me do that and that. Okay, this doesn't do what you think. Okay, and let me turn down the resolution. I think I need to do that. Yep, let's put the resolution at 40 and run it. All right, so we've got one kind of plane here, right? Okay, and what did we expect to get? Well, there it is. we have y is greater than 0 or y is greater than 0.5, right? So we sort of were expecting there to be two planes. We expected this relation, y greater than 0, to create a plane that was, on the xz plane at the intersection of y equals 0, right? We expected there to be a plane there and another one, halfway up. But there wasn't, right? And it doesn't have to do with the short circuit for OR. That's not quite right. Any other ideas? Any other ideas there why that might not work? Oh, there we go. Because the plane is just filling up half the space and it's only turned into a plane at the boundary between filled and not filled. Okay, yeah, that's right, Lucas. So the idea is you're trying to find these locations that are at a boundary, right? And remember, we were talking last week about these blocks, right? This whole world is made of these blocks, right? And you're only going to draw the blocks where some corners of the block are on one side of the boundary and other corners of the block are on the other side of the boundary, right? Well, what if I put in this as my relation? Well, it's only going to draw things on this side of the boundary. Why? Because the way that OR works, right? So it's saying, okay, well, I can be, let's use an example. I think that'll help, right? If you had a block that was, at 0.49 for one of the corners in the y-axis and 0.51 in another corner, right? So it straddled that boundary, right? That is some particular block, okay? Well, the problem with that is that all of those points are greater than 0, right? So even though it straddles this boundary, right, it doesn't straddle this boundary. It's just on one side of it, right? And so since this is just true, right, this is just, all the corners are going to be in the same, true for the relation, right? They're all going to have a y value greater than 0. Then in that particular case, this second part of the relation will never come into play. It'll never be in contention, right? Because if you had 0.49 and 0.51, you've already satisfied the relation here. Notice that this one does work. Let's think about why. So here you can have y greater than 0 or y is less than negative 0.5, right? You can't have a block that does both of these things. You can't have a block that has a y value greater than 0 and has y less than 0.05 at the same time. It's two totally different things, right? Two different sets. They're disjoint sets, exactly. Yep. So you can use OR if you have disjoint sets, right? But you can't use OR if the sets overlap, like these ones here, right? Does that make sense? People happy with that? Yep. Okay, good. So what do you do? So how do you make a union that works either way, whether the sets overlap or not? Okay, so you can go through and Lucas, like you said, you can go through and sort of wiggle it, right? You can sort of play with the numbers a little bit, right? You can also, try to arrange your inequality signs in such a way that you know, your different sets aren't going to overlap so that they are disjoint and it works. But it would be nice if we could have a union that works for sets that are disjoint or sets that are overlap, and it works either way. That'd be nice, right? How could we do that? Any ideas? Or should I give you the answer? Convert to the intersecting cubes before doing the union. I'm not quite sure what you mean by that, Lucas. Can you say more? Casting the int's not going to help. Lucas, I think you have the right idea, but I'm not quite sure what you mean. I'm not quite sure what you're saying. There we go. Good. Yes, you do have the right idea. So instead of putting the or right here, where the or should go is right here, right? If we intersect in some particular relation, or if we intersect in a different relation, right? And so what we need to do is make different intersects functions, right? And then or them together here in the if statement, right? Do you think we could do the ands up here in the if statement as well? Or should we leave the ands down here in the relation itself? Because it would be nice, right? Yeah, the and should be done in the relation itself. It would be nice if we could do all the ands and ors all in one spot, right? That would be, you know, sort of convenient to think all about the intersections and unions all in the same place. But I think, you know, well, I think we might be able to get away with doing the and up here, right? Because if we say, you know, you have to intersect this one and you have to intersect this surface, right? Is that going to mean the same thing? I mean, you could say it, but is that going to mean the same thing as say this guy, right? Not exactly, I guess, right? Because what we're saying here is we're saying, okay, well, you have to be less than 0.9, so you're going to be, you know, on that sphere, and you have to be greater than 0. So there, you're sort of, I guess I wouldn't really say an intersection exactly. Well, it is an intersection. It's an intersection of it's an intersection of two regions, right? Rather than two surfaces, right? So here you're saying, okay, well, there's this region of stuff that fills up a sphere. There's this other region of stuff that's bigger than, you know, on the plus side of the xz plane, y is greater than 0. And if you want both of those, then you're going to come out with, you know, a hemisphere, right? It's the half of the sphere that's above the you know, positive y values, right? Whereas here, if you used an and, it would do something, but it wouldn't do the same thing, right? Here, if you had an and, you would say, okay, well, you only have cubes that intersect this particular, that lie on this surface, right? And then if you said an and, it would have to lie on both surfaces rather than this and, which is saying a block has to be in two regions rather than on two surfaces. Does that distinction make sense? I was saying regions and surfaces, and I'm not sure if that's good terminology, if y'all are following. Okay. Cool. So any other questions there? Does that sound okay? All right. Well, we're an hour in. Makes sense. Great. Good, Tamara. Yeah, that was your question. Yeah, glad you got it. We're an hour in. Let's take a short break. Let's take 5. Then we'll come back and jump into the book. I'll see you soon. All right. So starting in on section 9.1, I'm going to begin as usual with a couple of definitions. So first of all, a sample space is the set of all possible outcomes of a process. I'll say of all possible outcomes. The outcomes of a process, of choosing things, outcomes of an experiment, it says, right? And an event is a subset of a sample space. Right? So can someone give me an example of a process, a sample space for that process, and an event in that process? Any ideas? Okay, so this is all really abstract, right? But it's saying something actually pretty straightforward if you can think of a good example, right? Okay, so there's your sample space. Flip a coin twice. Okay, so that's not quite the sample space. I would say that's the process, right? The process is flipping a coin twice. What would the sample space be for flipping a coin twice? Good. Heads, tails, heads, tails, heads, heads. All the different outcomes, the set of all possible outcomes of flipping a coin twice. Okay. An event, that you got right, get 2 heads, right? Getting 2 heads is a subset of the sample space, right? What's a different example of an event in that sample space? So for your particular event, David, there's exactly one outcome that satisfies that event, right? And Tamara, you had a question. Is sample space rolling a dice? Rolling a dice would be another example of an experiment or process, right? And the sample space for rolling a dice, if it's a normal cube-shaped die, would be 1, 2, 3, 4, 5, 6. Exactly. Yep, just what you said. Yep, that'd be the sample space. So, but can you give me another example of an event that might happen when you're flipping a coin twice? Other than just getting 2 heads, what's another example? Getting a heads and tails, right? One of each. And that particular event has 2 outcomes in it, right? Because you could get heads, tails if you flip the heads first, or you could get tails, heads if you flip the tails first, right? So in that particular case, the order would matter, right? Is everybody good on that? Any questions? Okay, makes sense. Good. So the probability of an event, P, is going to be the size of the event space divided by the size of the sample space. Okay. So what would be the probability of flipping a coin twice, getting 1 heads and 1 tails? half, right? So for example, flip a coin twice. The sample space is going to be heads, 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 tails, tails, heads, tails, tails. And the event space for getting one heads and one tails would be heads, tails, tails, heads. And we want to take the sizes of these guys divided by each other. So we'll get 2/4 equals 50%. What do you guys think? It's good? Let's do another example. Someone else give me a different, instead of flipping a coin twice, let's do a different process. Then we'll think of an event that might happen in that process and calculate its probability. So what's a different process we could think about? Okay, roll 2 dice, like Monopoly, sure. Instead of flipping 2 coins, we'll roll 2 dice. Okay, so to roll 2 dice, the sample space, or the size of the sample space, is going to be what? 36, right? 6 times 6, because you have 6 possible outcomes on the first one, 6 possible on the first die, right? 6 possible outcomes on the second die, and you multiply those. Why do you multiply those? Why don't you add them or subtract them or divide them or something like that? What's the reason for this multiplication here? Okay, that's true, right? You're doing 6 squared for 2 dice, but why? Like, why are you multiplying those 6s together? Okay, so for each way of getting an outcome with the first dice, there's 6 ways to get a second outcome. Yeah, good. So if you roll a 1 on the first dice, then there's 6 other things you can get on the second die. Sorry, I said dice. Dice is plural, die is singular, right? So if you roll 1 thing, you're rolling a die. If you're rolling 2 or more, then you're rolling dice, right? One little cube is not called a dice, it's called a die. So if you roll a 1 on the first die, then on the second die, you could get 1, 2, 3, 4, 5, or 6, right? Or you could roll a 2 on the first die and again get 1, 2, 3, 4, 5, or 6, right? So you're going to multiply these because for the 1 on the first die, there's 6 outcomes. It's like doing the Cartesian product. Exactly. Yeah, that's exactly right, Lucas. So there's even a picture of this in your book, which is kind of nice, right? So here's all the situations where on the blue die, you roll a 1, there's 6 of them, right? Or on the blue die, you could roll a 2, there's 6 of those, right? And so 6 ways to do the gray times 6 ways to do the blue, because you make this big table and it's just like the cross product, just like you said, Lucas. That's great. And in this particular example, these are colored die. So 3, 2, 3 on the blue and 2 on the gray is different than 2 on the blue and 3 on the gray, because the dice have different colors, right? In other words, order does matter in this particular example. Maybe with a game like Monopoly, order doesn't matter. You have 2 dice that are the same color, right? And it doesn't matter which die is which, right? It's just, well, you rolled a 10. It doesn't matter, if which one of the die was a 4 and which one was a 6. You just add them either way. It doesn't matter, right? But you could play a dice game where it does matter which die gets which outcome. Monopoly is just not that game, right? Okay, so there's our sample space, 36. What's an example of an event when you roll 2 dice? Now I'm doing it backwards the other way. Okay, you roll a particular number. Okay, so pick one. So what would you say? 7. Okay. So rolling a 7. So how many different ways can you roll a 7? Six ways. Okay. Let's see if we can find it here. So rolling a 7, well, there's 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. And so this diagonal here, the dice combination, the sum of the dice is equal on this diagonal. And you can see that for getting a 7, there's 6 different ways of doing it. Perfect, right? So to roll a 7, the size of the event space is 6. So what's the probability of rolling a 7? Okay, so remember the probability is the size of the event space divided by the size of the sample space. Very good, 1/6. Right? Or 6/36, which we then simplify. Great. Okay. What's another example of an event that can happen when you roll 2 dice? Let's do a few more of these. Snake eyes, double ones, right? So how many different ways can you get snake eyes? Which is a 1 on both dice, right? 2 ones. How many ways can you get that? 2. Very good, right? Because you can roll a 1 on the gray. Oh, uh-oh. I was going to say you can roll a 1 on the gray and 1 on the blue, and a 1 on the blue, 1 on the blue, 1 on the gray. Actually, that's just the same thing, right? Yeah, just 1, right? Yeah, very nice. A little sneaky there. Okay, so that would be 1 out of 36 chance, right? Your probability would be 1 divided by 36. Okay, let's do one more. What's another event that could happen when you roll 2 dice? You get an even number. Okay. Both numbers are even, or their sum is even, Luan? Because those would be different. Both even. Okay, great. So this one's a little bit interesting, right? Both dice even. Okay. So how many different ways can you get both dice even? Well, we could count 9 ways. Well, let me put our picture back on here. Okay, so we've got this column's out. This column's in, but we only get 3, right? We got 2 and 2, 4 and 2, 6 and 2. So there's 3 there. In this column, these 3, and in this column, these 3, right? So 9, I agree with you, right? If we just count them up. So the size of the event space is 9. And so the probability would be of both even is going to be 9/36, right? Okay. But there's another way of thinking about it, right? Yeah, and Sean, that's what you wrote down. That's perfect, right? So you can also think about it as the probability of getting the first dice even or the first die even, right? And getting the second die even as well, both of which is a 1/2 probability. And if you're doing and, you're multiplying. If you're doing or, you're adding, right? And that's the addition rule or the multiplication rule, okay? So if you want both things to happen, you have an and, right? And you're going to be multiplying those probabilities, which of course, 1/4 out of 36, right? 9 is 1/4 of 36, right? So you get 9 out of 36 the other way as well. What if we did an or? Let's do an or example. How about sum greater than or equal to 10? What would be the event space size for that? Yeah, there'd be 6 of them. Yeah, that's right, David. So why would there be 6? Well, it's the size of getting exactly 10, or how many different ways could you get 11, or how many ways could you get 12? You just add all those up. And this is terrible notation, but just bear with me, right? How many different ways could you get a 10? Well, there's 3 ways. You get 4 and 6, 5 and 5, or 6 and 4. Let me put my picture back up. So here is where you get 10, this diagonal here, 6 and 4, 5 and 5, 4 and 6. Or you could get 11, which would be 6 and 5, or 5 and 6, or you could get 12, which is 6 and 6. So 1, 2, 3, 4, 5, 6 total options for how to get 10 or more, which of course is going to be 6 out of 36, which is 1/6 for the probability. Right? What do you guys think? Questions? All right. So let's do some more examples. Okay, we're going to go back to coin tosses. Okay. All right, so these problems are from your book. Suppose the coin is tossed 3 times, right? And also assume that it's a fair coin. It's not weighted weird. So you're just as likely to get heads as you are to get tails. They have trick coins, right, that magicians or hustlers can use, where it's more likely to come out with heads, or something, because the coin is weighted in a strange way, which makes when you flip it, makes it more likely to come out heads, right? Okay, so in a case where we have a fair coin, we toss it 3 times. What is the well, first of all, what's the size of the sample space? Eight, right? 2 cubed, because you have heads or tails. You do it 3 times, right? So 2 times 2 times 2, 2 cubed equals 8. Beautiful. Okay. What is the contents of the event space for exactly 1 toss resulting in a head? So what's the event space for 1 head? 1 heads, let's say. 3 out of 8, good. And what would be its contents? What would be the actual members of the actual outcomes for that set? Good. Heads, tails, tails. Tails, heads, tails. And tails, tails, heads. Very good. Okay. What about the event space that at least 2 tosses have a heads? Okay, heads, heads, tails, heads, tails, heads, tails, heads, heads, and then all heads. Very good. 4 of them. Perfect. Okay, so you wrote it on the chat, so I won't write it again. And the size would be 4. Yep, exactly. Yeah, very good. Okay, how about that you don't get any heads? Yep, just 1. And what would it be? Tails, tails, tails. Good. Okay, heads, tails, heads. Cool. All right. Okay, let's try another one. All right. So this one's a little bit more involved. Let me put the text of the problem up here. So it's going to take a minute to describe. All right. So you have an urn, which is just a bowl, right? It's just a container, okay? It has 2 blue balls and 3 white balls. 1 ball is drawn, its color recorded, and is replaced in the urn. And then another ball is drawn and its color recorded, okay? So B1W2 denotes the outcome that the first ball drawn is B1 and the second ball drawn is W2. Because the first ball is replaced before the second ball is drawn, the outcome of the experiment is equally likely on each draw. List all 25 possible outcomes of the experiment. Okay, so rather than listing them, why don't you just describe them to me? So what would that sample space look like? Man, why don't you give me an example of one event in the sample space? How about that? Okay, blue 1, blue 2, right? Both balls are blue. You got both of those 2 blue ones, okay, and none of the white ones. Okay, another what's another outcome you could have? Okay, you could have blue, white, but it does want you to record which blue ball it is, right? So maybe you could have B2W3, or you could have B1W1, and that would be different, right? So I think in that case, Haruka, you'd want to say something like, you know, B1, B1, W2, something like that, right? So let me ask you, yeah, you got it, cool. So let me ask you a question. How many different ways could you get a blue ball followed by a white ball? Yeah, 6, very good. Because you could get 1 or 2 on the first one, and then 1, 2, or 3 on the second one, and 2 times 3 is 6, right? Cool. There you're multiplying because you're saying and, right? I want the first ball to be blue and the second ball to be white. Sorry, that's my dog. All right. How about the probability that the first ball drawn is blue? Be right here. What would that probability be? Yeah, 2 out of 5, right? Because when you draw the first ball, right, you have a 2 out of 5 chance of getting a blue one, right? 2 blues out of 5 total balls, right? Okay. How about the event that only white balls are drawn? What would that probability be? Three out of 25. 9 out of 25. Okay, which one's right? Okay, David, you got 3/5 times 3/5, and I think that's a good way of looking at it, because you have to draw a white ball first, and you have to draw a white ball second, remembering that they're replaced in the urn, right? So you got a 3 in 5 chance of drawing a white ball the first time, and multiply, you have a 3 in 5 chance of drawing a white ball the second time, since you put the first one back, whichever one it was, right? And if we actually looked through the event space for those events, you would see there are 9 different possibilities. Let's list them, right? So what are the 9 different ways that you could get 2 white balls? Very nice. 1, 2. Well, Sean, you got some of them. So you're missing 1, 1, 2, 2, and 3, 3, because you can replace them. Remember, replacement. There you go. Nice. And yeah, Nathan, you got it. Very good. Okay. Any questions there? Does that seem okay? All right. Well, let's move on to 9.2. Move that back over here. Okay. Great. All right, so 9.2 is all about the multiplication rule, which I was just saying, right? When multiple things need to be true, when you're anding them together, then you multiply all the different probabilities. So, for example, your book talks about a PIN number, right? And with your PIN number, there are, at your bank, usually they're 4 numbers long, right? So if you have a 4-digit PIN, how many different pins can you have? Ten to the fourth, right? 10,000, which is pretty easy to think about, because you can have 0000 all the way up through 9999, which of course is 10,000 different numbers, right? 9,999 plus the 0, right? You got to remember that off by 1 error, right? So 10,000 total. Okay, what if you had not just digits, but alphanumeric alpha characters as well, alphabetic characters as well, I should say. So for alphanumeric pin. Right? Would be 36 to the 4th, which is a lot more, right? A lot more. Let's see, 36 to the 4th, how much is that? That's 1.7, almost 1.7 million. Right? That's a lot. These combinations grow very, very quickly, right? And we're going to see why that is in just a minute, right? Okay, let's do another example. Let's do a 4 alphanumeric pin with no repetition allowed. So for example, you could have, A1B5, but you couldn't have A1BA, right? You can't repeat any letters or numbers. So now how can we compute this? Yeah, very good. 36 choices for the first one, 35, 34, and 33, because you use up one of your choices each time. Good. And another way of saying that is 36 factorial divided by 32 factorial, right? Because the way that factorial and division would work together here, you have all 36 numbers multiplied together, and you cancel out all the numbers from 1 up to 32, which just leaves you with 33 through 36 being multiplied, right? Yeah, very nice. Okay. All right. Let's do another one here. Okay, so here's a sneaky one, right? Okay, there are 3 officers to be chosen from 4 people: a president, a treasurer, and a secretary. And in this example, one person cannot be president, and 2 people, one of 2 people have to be secretary. So let's call these people A, B, C, and D. A, B, C, and D are picking president, treasurer, and secretary for their club. Okay, president, treasurer, and secretary, right? No, but there are some restrictions, okay? A can't be president. Maybe, Alfred is too busy and he doesn't have time to be president, but he could be treasurer or secretary, and that would be fine, right? Furthermore, C or D must be secretary. Maybe they're the only people that are interested in it, right? So how can we figure this one out? How many different choices do we have for who gets which position? Not exactly, not 2 times 2 times 2, because there are 2 choices for secretary, but there's more than 2 choices for treasurer or president, right? Oh, and also you can't have a person that holds multiple positions. So it's not like A could, it's not like B could be president and treasurer and secretary, right? It's got to be one person per position, right? So there is a 2 in there for C and D for secretary. Yep, I agree. Okay, so For secretary, there are 2 options. How many options are there for treasurer? Three times 3 times 2. Well, why would there be, well, I can see why there would be 3 for the president, because A can't be president, right? So I see the 3 here. But why wouldn't there be 4 for the treasurer? So Kobe, you think there would be 4. And you think, Nathan, you think only 2 for the president. Well, why would that be? Only 2 president, because when we pick the secretary first, there's only 3 left. But A can't be president. Oh, I see. So you're thinking we should decrease the numbers here rather than just doing the total, right? So here was my idea, right? 2 for the secretary, 3 for the president, 4 for the treasurer, but you're saying that's not right. We're supposed to be decreasing the numbers each time. Okay, so if we have 2 for the secretary, then we would have how many options left? Yeah, we really do need the tree thing, right? So what you're describing, Sean, is a probability tree, right? Or a choice tree. I think your book calls it what do they call it? I believe they call it a probability tree. Doesn't say. Okay, that's fine. Call it a probability tree. So at the very first choice, let's choose the secretary first, right? So the secretary choice, we have 2 options. We could pick either C or D, right? Okay, so let's fill out this tree. So assuming that we pick Carol for secretary, what are our remaining options? A, B, or D. Okay, so who are we picking next? We're picking the treasurer next. Any of the remaining 3 can be treasurer, or we should pick president next. Well, maybe the president has restrictions. Yeah, so maybe we should do the president first, since the president has a restriction. We'll get rid of the restricted things first. Okay, so if C is secretary, then who could run for president? B or D, okay? So we can go B or D for president, and then treasurer is last, right? So how many choices would there be left for treasurer? 2, right? Here we've used B and C, so the treasurer could be A or D, right? Here, C and D have been used, so for the treasurer, we would need to do A and B, right? Okay, what if we take D as our secretary? Then we could pick president next, which would be, well, D is done and A can't be president, then that just leaves C or D for president. And then if D and C are used, who can be treasurer? Well, that would be either A or B here. Oops, sorry, it can't be C or D. Sorry. It'd be C or B, pardon me. There we go, that's better. C or B, right? And then here we would have A and B are used, so A and C would be left. Okay. And we did end up getting 8 total picks, which is 2 times 2 times 2. So it is 2 times 2 times 2. Interesting. Well, what if we tried to make a different tree? So I know someone, Sean or David, Sean was saying we should do the treasurer and then the president last. Okay, so let's try it that way. Let's do secretary, then treasurer, then president. Okay, so the secretary, again, could be C or D. Okay, then the treasurer could be what? So C is the secretary. Who can be treasurer? A, B, or D, okay? Okay, and what if D is president? Then we would have A, B, or C for treasurer, right? Okay. So if C is secretary and A is treasurer, how many choices do we have for president on this row? B or D, right? Here we've got B or D for president. Okay, what about here? We have C is secretary, B is treasurer. Who do we have left for president? Well, C's already been used. Yeah, only D, because A can't be president, right? So this would just have one line coming out, D, right? Same thing here, right? C and D have been used. The only person left is B, right? So there will only be one choice since A is not allowed to be president. Here, again, we'll have two choices for president, which would be B and C. But here, since A can't be president, we only have C left, and here we only have B left. So again, we have 8 total, right? But the tree looks a little different in that case. What do you guys think? Make sense? Feels like the fact that it ends up is just sort of a coincidence of the restrictions, not a rule. I agree. Yeah, that's just a weird consequence of the rules that we had, rather than anything deep or interesting going on. Yeah, that is true. Nice. Okay. So let's go in with another definition here. A permutation of a set is an ordering of the set elements. Okay. And if you have a set of size, you have a group of, let's say, n items, right? So the size of your set equals n. What's the number of permutations of your set? N factorial. Very good, right? Let's do an example. Let's say that you had the set 1, 2, 3, and you wanted to know how many different orders there would be. Well, you could have, let me say, goes to, it's not really equal to. From 1, 2, 3, we're going to make some orderings, right, of the permutations. Okay, so we could have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. 6 of them, right? 3 factorial equals 6. The way of thinking about this is saying, okay, I have 3 slots, right? We're going to think a lot about slots in the coming problems. Okay, we have the first, second, and third slot. Well, when we put something in the first slot, we could put 1 or 2 or 3 in here. So there are 3 options, right? But once one of these numbers has been used already, has been chosen to live in the first slot, well, there are only two options left for the second slot and only one option left for the third slot. So we have 3 times 2 times 1 equals 3 factorial total orderings. Yeah? Questions? All right, so your book has an example here. If we've got all the letters in the word computer rearranged, how many different anagrams of the word computer are there? So an anagram is a reordering of the letters. So can someone give me an example of an anagram of the word computer? Retube mock. M-O-C. Sorry, there's no A in computer. Computer mop. I like that one. That's almost English. Anyone see any English anagrams in the word computer? Yeah, I don't see any. I don't see any English ones. There's almost crumpet, but not quite. Okay, so those are some anagrams of computer. How many anagrams of computer would there be total? Yeah, good, 8 factorial. Which is how much? Let's see here. 40,320. All right. So a lot of different anagrams of computer. None in English that I saw. Okay, let's do another example, right? Let's take the word, I don't know. Let's say anagram. How many of those would there be? Sean, Metro Cup, I like that, right? Maybe you could sit on your computer there at Metro Cup, right? Be one of those coffee shop laptop people. Maybe they have a cute mop there that they clean up the coffee shop with. All right, so what about anagram? How many anagrams of anagram are there? So what's just the naive answer? Yeah, okay, 7 factorial, right? Divided by something. Now it's not divided by 7, not quite. What's the idea behind your using division there? What are you trying to accomplish by dividing by something, David? Okay, to get rid of the A's, because if I have, you know, A, N, G, R, M, right? Well, that's going to be the same as if I switched these two A's with each other, right? So the order doesn't matter for the A's because they're the same letter, right? And so, you know, no matter what order I put these A's down, they're all the same. So those won't be distinct anagrams, right? They'll all be the same word. So I do want to divide by something. What am I going to divide by? Not 7, but you're close. Yeah, 3 factorial, good. Because there's 3 A's that could be in any order, right? So their order doesn't matter, right? Yeah, that's right. That's the number of ways to arrange those A's. So for every anagram that we do, this one, or, you know, if we want to say N-G-A-A-R-M-A, Nagarma, right? Then in this case, you could switch these two A's with each other, right? You could switch these two A's. Again, you can switch any of the A's in any of the orders, right? So there's for every anagram that you make, you're losing 6, you know, well, 5 out of the 6 ways that you could arrange those A's are going to be repeats. And so you don't want to count them, right? In other words, you're dividing by 6, right? Because you only get one distinct anagram for every rearrangement of A's, of which there are 6 of them, right? So this particular example would be 7 times 6 times 5 times 4, 20 times 42 makes, I don't know. My brain's not completely working today. That's 20 times 42. Why is Google not working? There we go, 840. Good. Cool. All right. So let's try one that's a little bit more challenging. How about anagrams of Mississippi? Oh, and we're at 3 o'clock. So how about this? Why don't we take another 5 minutes, take a little break, and then we'll come back and talk about the anagrams of Mississippi. Classic problem, right? So we'll be back in 5. See you soon. So did anyone figure out how many anagrams of Mississippi there are? All right, cool. 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Because you have 11 letters to start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. 4 I's, 4 S's, and 2 P's, right? So you have the 4 I's, that could be interchanged, 4 S's that could be interchanged, and the 2 P's that could be interchanged. Perfect. So how many is that total? Let me pop over to Google here. $36,650. Cool. All right. Let's do a little bit different kind of problem, right? Let's say that we have a round table. And so this is going to be kind of a similar situation, but a little different. So you have a round table with 6 seats. And you're wondering how many different ways can your dinner guests that you're going to have, your 6 people over for supper, right? How many different arrangements, seating arrangements can you have for your 6 people? So what do you guys think? So it only matters, who they're sitting next to, not the exact position. Yeah, Natasha, it is 5 factorial. How'd you get that? That's Sean's question. Sean asked the right question, and then Natasha, you got the right answer. So what exactly happens there? Again, y'all feel free to hop on the mic at any time. Okay, fix one person in a spot, and how can you arrange the other 5 around them? Okay, I think that's a good way of looking at it, right? Another way of looking at it, which turns out to be the same thing, is arrange the 6 people however you want. But if you have, A, B, C, D, E, F, like this, right? If you rotated everyone by 1 chair, so it went F, A, B, C, D, E, right? So you just took the whole table and sort of turned it. Everyone would still be sitting next to the same people, right? But that in that new arrangement, everyone would be sitting next to the same people, but the whole arrangement would be rotated, right? So another way of thinking about it, exactly, is 6 factorial divided by 6. Yeah, exactly, because there's 6 factorial total possibilities, and for each possibility, there's 6 different rotations that turn out to be pretty much the same thing, right? Which of course is 5 factorial. Nice. Okay. Any questions about that? Does that look good? Another sheet over here. It's a little wrinkly, but I think that's okay. Oh, question. So seat A is 1 person. Seat B could be any other person. Yes, exactly. Yeah, that's right, Tamara. Yeah, that was Sean's first idea of how to do it. Yeah. Okay, so let's do another definition here. An R permutation is R objects taken from a set of n objects. Right? And the way that you represent this, P of Rn would be what? What formula would we want to use here? Yeah, that's exactly right. And you can think about this in terms of those slots that I was talking about before. So if you have R slots, R objects taken from a set of n objects, those are your options. On the first spot, you can do n, then n minus 1 remaining, then n minus 2, and so forth, all the way down to n minus r, right? And you're going to be multiplying these because it's going to be and, right? And so that's going to be, that product, of course, is going to be equal to n factorial, which is n times n minus 1, blah, 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 but without the final r factorial of them, right? So you're going to be dividing by n minus r factorial, which would be all the other slots afterward that you don't get to fill in. Right? The remaining n objects that don't get to go in a slot, there'd be n minus r of them, and that needs a parentheses. Make sense? Any questions? Oh, I did screw something up. That should be n minus r plus 1, actually, in that last slot. There we go. That's better. Yeah, plus 1, right? Yeah, because here there are no r's. So this would be like R0, then R1, R2, all the way up to R, all the way up to R minus 1, but it's minus a minus, right? So that turns into a plus, right? Double negative there. Does that make sense? Questions? Sorry, we'll mess up there. All right, looks good. Okay, so let's do some problems, right? Quite a few problems here we can mess with. Okay, that's a good one. All right. Yeah, cool. Let's do license plates. Great. So we have license plates. Oh, I always misspell license. L-I-C-E-N-S-E. Which have 4 letters and 3 numbers in some particular state. Not in Oregon. In Oregon, we don't have this rule, but maybe some other state has this rule. 4 letters, 3 numbers. Okay. Then 3 numbers. Okay. How many are there total? All right. Not quite, David. That would be without repeats. So we're actually going to do that one in just a second. But if you do allow there to be repeated letters and numbers, then Haruka, you would be right. 26 to the fourth times 10 cubed. But without repeats, then David, you would be right. 26 factorial divided by 22 factorial times 10 factorial divided by 8 factorial, 7 factorial. Right? Okay, let's do another one. How about start with A and end with 0. With repeats allowed this time. You can have repeats. Close, David. So remember we have 4 letters. Yeah, the first should be 3. Yeah, very good. Good. So 26 cubed times 10 squared. Cool. Okay. How about plates that begin with TGIF? It's a vanity plate, right? Should be 0. Fair. Most vanity plates are pretty terrible. 10 cubed. Yeah, it's not a very good vanity plate because 6 days out of the week, it's kind of stupid, right? You only have a 1 in 7 chance of your vanity plate actually working if it's TGIF, so not a good one. Okay. Okay, that's fine. I think we got that one. All right, so this one's going to be interesting. Okay. We have set A. The size of a set A equals n, and the size of a set B equals m. Okay. How many relations are there from A to B? So first of all, what's a relation from A to B? What does that mean? Not quite. Not n by m factorial. Okay, a set of ordered pairs with one number from A and one from B. Okay, a subset of A cross B, right? Okay. So how should we think about this? Right? We have these different relations, right? So let's do an example. I think yeah, it's going to be the power set of A cross B. Something like that, right? Okay, so let's think about this. So let's say A is, 1, 2, 3, and B is 4, 5. Okay. What are all the possible pairs that could be in the relation? or how many possible pairs could be in the relation? How about that? Not 3 times 4. Close. You're one too big on each number there. Three times 2, right? 3 items here, 2 items here, because you would have, 1 4, 2 4, 3 4, and then 1 5, 2 5, and 3 5. So 6 total. You got it. Okay. Now all of these guys are what could be in the relation, but not all of them have to be, right? In fact, for each pair, you could choose whether or not to put it in the relation. So can you see? Yeah, there we go. Very nice. So we'd have 2 to the nm relations total. Right? Or if you want to say it, without the n and m, I think that's fine. You'd have 2 to the size of a times the size of b. Supposed to be a dot in there. Right? Okay. So let's try another one. F is a function from A to B. How many possible functions are there? So now we have some rules, right? Let's do another example. So we've got A and B here. Here's 1, 2, 3. Here's 4 and 5. But now that it needs to be a function rather than just a relation. So rather than picking whether or not each pair is included, we're going to be picking some new stuff this time. So what are we picking here? Pick an element in B for every element in A. Good. So on this first one, we have to have exactly one arrow coming out. That's the rule for a function. Each of 1 and 2 and 3, each one of these has exactly one arrow. So how many different arrows do we get for different possibilities for arrows for item 1? 2, right? So we have 2 possibilities here because we could go there or there, right? We have, again, 2 possibilities for 2, 2 possibilities for 3, right? So in general, how many possible functions can you have given the size of the set A and the size of the set B? Not cross, not quite. Yeah, not multiplied. Well, there's going to, in this particular example, there would be 8 of them, right? Because you have 2 options here times 2 options here times 2 options here. A to the bth power. Almost. You're almost there. Other way. B to the 8th power, right? The size of the set B raised to the size of the set A power. Struggle busing it. Yeah, me too today. Yeah, I'm tired. Does everyone see that, right? Because we got the size of B multiplied by itself an A number of times. Yeah? Make sense? Any questions there? Okay, how about this? How many possible one-to-one functions let's do a little bit bigger example. I think that'll help. So let's think about this. So we've got like 1, 2, 3, 4, 5. We're not going to count them all. I'm just going to try to get an idea for how many options we have, right? And with a one-to-one function, what do we know about the sizes of the domain and codomain? What if I had 1, 2, 3, 4? They don't have to be the same. You're almost there. Yeah, A has to be greater than or equal to B, not just equal. Yeah, good. Because if we don't have enough here, right, then, we'd be assigning things, like 1 goes to 3, 2 goes to 1, and we'd run out of stuff. And we couldn't put 5 to any of these other guys because then it wouldn't be one-to-one anymore, right? So B has to be at least as big as A in general, for these one-to-one functions to even exist at all, right? So assuming that the size of B is greater than or equal to the size of A, we're just assume that, then how many possible one-to-one functions would there be? Oh, you had it the wrong way. Yeah, that's right. Yeah, B has to be greater than or equal to A. That's right. Mm-hmm. So now let's think about choices, right? For 1, how many choices do you have? B choices, right? So B choices for number 1. How about number 2? B minus 1, right? And then, of course, B minus 2, etc. Going down. Okay. So, and we're going to multiply all these, right? So how many possible one-to-one functions are there? Good, right? The R permutation, that's exactly right. B factorial divided by B minus A factorial. Very nice. Okay. Well, let me ask you an interesting one. How many possible onto functions? So in that case, I guess we'll assume the size of A is greater than or equal to the size of B. Well, before we do onto here, let's do bijective first. We'll save onto for last. How many possible bijective functions where A is equal to B? The sizes are the same. A factorial, very good, right? Right, because we would have A is equal to B, so we would have B choices here, then B minus 1, B minus 2, and we would run out at exactly the same time that we ran out on the other side, right? So A factorial, perfect, or size of A factorial, or size of B factorial, they're equal, right? Okay, so now let's try onto, right? So we'll say A is greater than or size of A greater than or equal to the size of B. How many possible onto functions? Okay, so let's make another little picture here, right? So now we have in A here, let's have 1, 2, 3, 4, 5. And in B, let's have 1, 2, 3. Let's have 1, 2, 3, 4. So now what do we do? Or maybe a better question, what are we picking now? Reverse of 1 to 1. So you mean sort of like this thing, but we're switching out A and B? So say a little more, David. I'm not quite sure what you mean by reverse. Yeah, okay, that is what you meant. Not quite. Yeah, that's not quite it. Each element B for every A. Okay, so here's A, here's B. Okay, so you're saying for B, you're picking which A maps to it. Is that right? Like for one element of B, we have S choices. Oh, 5 choices. Right, I agree with you, right? So for this one, something's got to map to it because it's onto. So we have 5 options here, right? Okay, well, what about 2? Well, we don't have 5 options anymore, right? How many options do we have now? Now we have 4 options because we've already picked one of the things to map over to the 1, right? So it looks like we have 5, 4, 3, 2, which is the reverse of what we had here. I guess that's what you were saying. That's David. Wait, nope. Yeah, David. That's what David was saying. The reverse of what we had here. But is that right? Then we're forgetting the last one. Yeah, good. Because the 5's got to map to something, right? Yeah, there can be multiple lines, right? So here we have 5 options, right? We can pick any of the 5, but once we've mapped one of them, well, we can't map the 4 anymore. It's done now. So we do have 4 options remaining on the 2, right? And then we have, right? So we have these 4 here. Let's just fill it in, right? We have 3 options on the 3. Let's pick the 5, pick the 1 going to the 4, and then the 3 can map to anybody. So we have an extra 5 options. So would it be 5 times 4 times 3 times 2 times 5? Is that the right way of doing it? Or maybe a different way? Okay, you thought for a non-two function, each element of B can map at the same element of A. I'm not quite sure what you mean by that, Nathan. So each element of B has to have at least one thing that maps to it, right? So you can see 1, 2, and 4, those all have one thing that maps to it, but 3 has multiple things mapping to it. And at the same time, you can only have one arrow coming out of each element on A, right? Why wouldn't we add 4? I'm not sure what you mean by that, David. Instead of 5. Oh, I see. Right, because on that last one, you can pick any of the 4 to map 3 to. Yeah, you're right. Yeah, there'll be an extra 4. Thank you. No, you're right. Extra 4. Yeah, good point. Yeah, because there was this last 3 that was left off. We have 4 options for it, right? Okay. So we would add on B, yeah, the size of B minus A times the size of B, right? Because we're asking how many leftover A's are there, right? And then for each leftover A, which would be, actually that would be A minus B. Yeah, exactly. Yep. No, we're getting there, right? For A minus B, that would be however many extra A's there are. There would be B possibilities for where to map it to. Yep. So let's think about order for a minute here, right? So in terms of the choices here, have we covered all the choices for B and how to map them? Like when, you know, when we say what maps to 1, we have 5 options, right? Is that true? No. Okay, why not? We have more. Okay, how do you mean? Maybe we should do another example, right? I think maybe that'll help. Let's try a bigger example. So here's A and B. Okay, so let's see if our idea works in this example, right? So here we would have 7, 6, 5, 4 as the numbers here, right? And then how many extras? There would be 3 extras on A with 4 choices each. And actually, I think we'd be multiplying that rather than adding it, right? Because, you know, that would be multiplying. You're saying, you know, these are what map to B, and this is what the extra elements map to. So I think that this would be times and an additional 3 times 4 at the end, right? Which is fine. Okay. But I think, David, you're still saying that that's incorrect. You think there are more? Okay, why is that? Start from 7 instead of 1. You mean start from here? You don't know. Okay. Well, how about this? We're almost out of time here. Why don't I let you guys think about this, right? How many possible onto functions there would be? I think it's a nice little juxtaposition of the the last couple chapters of different things we've been working on, right? Relations, functions, and probability all sort of rolled together into a single question, which is always nice. Just so you know, that's what I like to do on exams. I like to take you know, topics from multiple chapters and combine them into a single question. So you should expect that on your midterm and final, kind of pull things from all over and combine them together. I think that makes it for an elegant problem, right? So what do you guys think about this, right? If you want to do some research, of course you can do that, and the internet will have the answer for you. But you know, yeah, I think it would be a fun little problem to think about. And that's all I have for you for today. Does anyone have any questions for me before we go? Not from you? Going once, going twice? All right. Sounds good. Well, have a great day, everybody. I will see you on Wednesday and talk about some on-to functions. All right, have a good one, guys.